In this segment, we'll look at enum column types and the various ways to design them. In almost any software application, one encounters enumerations, variables that take on one of a fixed list of allowed values. Classic examples include a variable holding a day of the week, which is of course one of 7 possible values, or a student's class standing, perhaps 3 to 8 possible values depending on the application, or a U.S. state, one of 50 possible values. Programming languages often provide a means of declaring enumerations or enum types. Java, C, and C++ enum types are typical examples. Here is a C++ enum declaration, for instance, and Java's would look similar. Now, under the hood, enum variables are usually implemented as integers, with integer constants for each allowed value, and compiler enforcement of the use of the constants, rather than arbitrary ints. In the C declaration here, for instance, is just a constant name for 0. Monday is a constant for 1, and so on. Now, the values allowed by a given enum are also ordered. An enum for days of the week might be ordered, as you see here, Sunday through Saturday. And this makes comparison possible. Sunday is less than Tuesday is true, but Thursday is less than Monday is not. It also allows loops through the values in a predictable order. Especially when an enum is implemented as an integer, this ordering follows naturally. Input and output of enum values can be problematic. First, an enum value like Sunday is a language internal variable name representing an int, not a string. So translating this to and from the string Sunday takes handwritten code in most languages, and translating it to or from Sunday or Domingo or Sonntag, depending on the language of the user, is even more complex. Even for just a single language, one ends up with code like this, where we have to compare for each value and then print the appropriate string depending on the enum constant. So, as we look at representing enumerations in a database column, remember these 3 design goals for enumerations. First, we need a way to ensure that values assigned into an enum column are one of the allowed set of values. And then second, we need an order or a sequence for the allowed values of an enum column. And then third, we need a way to translate enum column values to or from readable strings, preferably internationally. And with those conditions in mind, let's look at the 3 ways one can do enums in a database column, all 3 of which are illustrated in the attached enums.sql file, content from which is up here on the diagram as well. This declares several different enum columns to represent a choice of shirt color. The simplest approach for storing an enum in a database is to declare an int column and use a different integer value for each enum value. We might, for instance, declare a column day of the week and make it an int and then use 0 for Sunday, 1 for Monday, and so forth. In enums.sql, in the first line of shirt, we declare such a column for color. And there's even a little reminder comment here that says how to use the column for the 4 colors we want to represent. Now, this seems like a cheap and quick approach, and it only clearly meets one of the 3 criteria that we gave for our design goals. And question 1 is, which of those 3 criteria is met by this approach? And the answer is criterion 2. Integers clearly have an ordering, and so that's met, but the other 2 criteria, not so much. There's no enforcement for putting a valid integer into this column. We could put 100 in there if we wanted to, and there's no clear way to translate to and from the int value to a string in the appropriate language. So this approach doesn't work all that well for textual interaction via clients like MySQL. The database user is required to remember the integer equivalent of each enum value. Let's see, blue is 1, no, that's 2 actually, and so forth. And then not to mess things up. What do you mean there's no color 5? However, in practice, over 99% of database interactions are not done via text clients. We use the MySQL text client in this class to learn SQL, and because it's simple and direct, and because it's an important debugging and administration tool for serious database devs. But mere mortals always interact with the database via a program, a web app, a mobile app, or even an old standalone desktop app. Any direct textual interactions are usually done by serious developers or database administrators who can put up with an unfriendly integer representation of enums. If it's a program that's reading and writing the integers from and to an enum column, then the program can automatically translate the integers into their enum equivalents, usually very easily. Plus, at least some of these languages, like Java, have powerful internationalization tools, allowing you to do table-driven translation from internal enum values to human-readable strings in a variety of languages. And most languages refuse to allow invalid values in enum variables. So the underlying philosophy of this first approach, and I'm going to keep a little tab of them here, which we might call enums by integer, is to put the enum values in the database as simple integers, which permits any desired SQL comparison or search if you can remember what the integers mean, and then let the client software deal with giving meanings to the integers, making the I/O pretty to the user and preventing invalid values. And anyone talking directly to the database in SQL should be enough of a geek not to be intimidated by integer enum values and to get them right. But there are problems with this method. Say I have a C app with the enum, and I've got an example down here, red, green, blue, yellow, matching our database column int color with its expected integer values, 0 for red and 1 for green and 2 for blue and so forth. So what's wrong if let's assume I need to update the app and I have to drop green as an option here. And instead I'm going to add purple and puce. So what's wrong with just redoing that? And let's kind of keep the red in there, and we'll add puce and purple, and there we're good. And what would you need to do, first, what is wrong with doing that? And then what would you need to do instead to minimize problems with this change? If you think about it, changing the enum in the program means that the underlying integers now have different meanings in the program. 1 now means, or 0, I'm sorry, now means puce, for instance. So if you just make this change in the program without adjusting the database contents, then all the 0 values in the database suddenly represent puce in the program instead of red, and all the 1 values signify purple instead of green, and so on. Unless you change the database contents, the only modification you can make to an existing enum type in a client program is to add new value choices to the end of the enum, and that's how you'd make this happen correctly. What we would have to do is keep it as red, green, and blue as we had before, and then add in at the end puce and purple. Now, even if you no longer want a choice of green, you'll have to keep it to avoid shifting blue and yellow downward. Or you can, of course, modify all the database enum columns to adapt to the new enum sequence as part of the new release. But God help you if you overlook this and then run under the new enum value in the program with the old database values and end up with a database column having the same old 0 values that were supposed to mean red and others that are new and that now signify puce. So let's try another design option, what we'll call enums by lookup table. This design approach takes the opposite view, with the database holding all information needed to interpret the meaning of each enum value. This approach maintains a separate lookup table of allowed enum values. For instance, for our color example, we have a lookup table, color, with a row for each allowed enum value. And you can see when we get to an insert statement, that'll be clearer later, but for now it inserts these rows into that colored table. So when we load the enums.sql file, as I just did here, and do a select star from color, we get this following display. We still use an integer column lookup color for the enum in shirts, right there. just as in the enums by integer approach. But this column is a foreign key into the lookup table. So it may only take on values matching one of the IDs in that table. And that makes it possible to translate SQL that would have been something like select description from shirt where int color equals 2 into something that doesn't require knowing that 2 means blue. And then question 3 is make that translation. Write a query using table color that has the same outcome as select description from shirt where int color is 2, getting shirts that are blue in other words, but which doesn't require the user to know the integer value for blue, instead letting him or her use the string quote blue quote for the search. So what we need then is a join operation. We're going to select description from shirt comma color, where lookup color equals color.id and then name equals blue. So at the cost of a join, we get rid of that geeky remember that 2 is blue requirement. And the fact that shirt.lookupColor is a foreign key means that the database will prevent us from inserting a value, like 10 maybe, that doesn't correspond to the ID of a row in color. So question 4 then, how many of the original 3 criteria over here does this method, this enums by lookup table approach, satisfy? And the answer is it satisfies about 2.5 of them. It enforces the right enum values. It allows ordering of enum values. And it provides a user-friendly string representation of the values. The missing 1/2, though, is internationalization. Okay, so let's fix that. By a reasonable augmentation of the color lookup table, you can add internationalization so that one can, for instance, search for green in English or verde in Spanish. Let's assume that there is some standard 2-letter abbreviation code for different languages, which in fact there is. And let's assume the abbreviation for English is EN and for Spanish is ES. So with that, adjust color so that I can search for a color in whatever language I want, given the color string and the language string, the language abbreviation. I might search then for verde in ES or for green in EN and get the same set of shirts. This will take one new column added to color and show the representative contents for that column as part of your answer. So by way of answer, I'm just going to drag the notes into the visual area here. And this is what we kind of need to do. We're going to add a language column to color. Call it lang. And for each enum value, we need a separate color row for each language that we support. And note, by the way, that this means that enum columns referencing color from other tables are no longer strictly foreign keys. Value, say, 1 might now signify several rows in color. An ID is not a unique primary key. But we'll have a 0 for EN and red and a 0 for ES and rojo and so forth. So question 6, write 2 shirt queries that get the descriptions of blue shirts, one query in English and the other in Spanish, assuming this new color table, of course. And the way you do that is in English you do a select description from shirt and color, where lookup color equals color ID and then lang equals EN and name equals blue. Or you could have lang equals ES and name equals azul. The enums by lookup table design is pretty powerful, and it's favored by the databases are the main event and apps are a sideshow lobby. But it has its weaknesses too. And I'm sure you won't be surprised that question 7 then is to briefly critique enums by lookup, and what weaknesses do you think it has? By way of an answer here, for starters, every use of an enum entails an extra database join with the attendant time consumption. Remember, 4 years per disk fetch in CPU time. This is ameliorated somewhat by the likelihood that the lookup table will be memory cached due to frequent use. But still, extra join. Also, the lookup table doesn't really preclude the need to modify the client app software if the enum changes. Technically, an app could automatically adjust its menus, its checkboxes, and so forth based on the contents of the color table, but in practice there will always be some changes that can't be fully table-driven by the database. So, because of these weaknesses, the enums by integer design is favored by the apps are in charge and databases just hold persistent state lobby, and have augmented our two enum methods with those design philosophies. Neither group is fully correct. The right choice depends on the context. Now, a final point here, MySQL, not SQL, but MySQL, and for that matter, many other database management systems, offer a compromise alternative. A built-in enum type, a column type, that lists the allowed enum values directly in the declaration. So this third line in shirt.sql create table, shirt is an example. Built-in color enum, red, green, blue, and yellow. It treats such a column as if it were a string with a fixed set of allowed values. So you can write where color equals, quote, blue, quote. But it's stored as an integer with the values of 1, 2, 3, and 4 for the 4 color choices. The value 0 is reserved for an error indication, so it prints as an empty string. So it's as if you really automatically got a color table with content, again drawing from the transcript, like this. 0 for empty string and then 1 for red, 2 green, and so forth. If you try to assign an invalid value into an enum column, like chartreuse, then it gets automatically converted to the empty string error value. And that allows post facto detection of errors if bad values are assigned. So if you insert a bunch of rows, you can then check for a built-in color equals empty string to find errors. Again, the underlying implementation of an enum column is still an integer, and you can even address it that way. You can ask if built-in color is equal to 1, and that's the same as asking if it's equal to, quote, red, quote. In effect, an enum color, or an enum column, creates a virtual color table, though not an actual one, and then automatically joins that virtual table when you use strings for enum values in assignments or in comparisons. You can even name the enum type itself, so you can call it a color type by adding that in after enum. Thus, color type becomes a user-defined column type, which you can then use in other column declarations, so they all stay synchronized to the same choices. So in another table I could write pants color, color type, and in effect they'd all use the same virtual color table. Okay, so question 8. Critique this design alternative. How does it do against the 3 criteria, and what are its weaknesses, if any? And by way of an answer here, one problem is that it doesn't support internationalization. And app software working with the enum doesn't have a ready way to get a list of all the enum choices, as it would with an explicit lookup table, or its own internal enum. The MySQL manual offers the helpful suggestion that you can do a show columns call and then parse the enum column declaration to get the allowed values. Yeah. So one could argue that error handling is weak. Silently accepting bad values and converting them to blank for later checking, that invites leaving unchecked errors. Although MySQL at least does supply a server flag that shuts down that behavior, turns it off, and replaces it with an immediate error message if you want. Frankly, though, this supposed compromise solution, like many other compromises, doesn't please everyone, and it probably has as many outspoken detractors as either of the other 2 design approaches. But it's still worth knowing. And if you want to see a real nerd fight, make a Stack Overflow post asking which of these 3 methods is best. So you've now seen all 3 major solutions to the enums in databases problem. And which one you choose depends on your particular application, your design aesthetics, and most importantly, whatever is standard in the shop you're working in.